Have you ever wondered how a robot arm precisely places an object, or welds a delicate seam, without crashing into its surroundings? Its smooth, coordinated movements are not accidental, but rather the result of carefully managed velocities, often understood into fundamental ways. The core difference between joint space velocity and task space velocity lies in their frame of reference. Joint space velocity describes how quickly each individual joint on a robot arm is moving, typically measured in degrees per second or radians per second for rotational joints, or meters per second for prismatic joints. In contrast, task space velocity describes the linear and angular speed of the robot's end effector, such as a gripper or tool, relative to a fixed world coordinate system. Imagine one as the speed of each limb and the other as the speed of the hand itself. This distinction is crucial because a robot controller needs to translate desired end effector movements into commands for each joint. The underlying reason for these two representations is the robot's kinematics, the mathematical relationship between joint angles and the end effector's position and orientation. Changing the speed of a single joint in joint space will affect the velocity of the end effector in task space, and this effect changes depending on the robot's current configuration. This intricate relationship is precisely described by a mathematical tool known as the Jacobian matrix. To effectively control a robot, understanding both is vital. When you program a robot to follow a straight line or apply a constant force, you are typically defining its motion in task space. The robot's controller then uses inverse kinematics and the Jacobian matrix to calculate the necessary joint velocities to achieve that desired end effector movement. Conversely, directly commanding joint velocities might be simpler for basic movements or for avoiding joint limits, where you prioritize the individual joint speeds rather than a specific end effector path. One insider detail is the concept of kinematic singularities, which are configurations where the Jacobian matrix loses its invertibility. At these points, a small task space velocity can requiring infinite joint velocities, leading to control issues or even damage. Understanding both velocity types helps engineers design paths that avoid these problematic areas. Another crucial aspect is that task space velocity allows for intuitive human interaction or path planning, as humans naturally think about objects moving in three-dimensional space, while joint space provides direct control over the physical actuators. Mastering the concepts of joint and task space velocity is fundamental for any roboticist aiming to program precise, efficient, and safe robot motions. It provides the essential framework for translating high-level task requirements into the specific joint commands that bring a robot to life, ensuring it moves exactly where and how it needs to go, avoiding pitfalls and performing complex operations with graceful precision.
If you love robotics, like, subscribe, and keep building with us.